I'll come back. I want to go over the homeworks on 7.4. And although this is in the chapter of power series, it's actually in this, what we do with it is nothing to do with power series. So we have, I remind you, we have these equations of the form. So these are the called Euler equations. And typically, therefore, is they're not constant coefficients, but they have a to the x squared, b, x, and c. So this is degree 2, degree 1, and degree 0. And so matching the order 2, order 1, order 0. And then what we need to do, so this gives me the initial, we have the initial polynomial, which is, should not be confused with the characteristic polynomial, which is, or equation, which is very similar, but this is a, what we used, r or t, I forget now, I'm going to use t. T times t minus 1 plus bt plus c equals 0. So the only difference is really, instead of a t squared, we have an a t minus 1. But of course, the difference is also that this is not constant coefficients. That's why it's different. Okay, and then we look for roots of this equation, and that, again, these roots could be three cases. There's the discriminant is positive, discriminant is 0, or the discriminant is negative. And they each have their own type of solution. So let's go over two at least of them. So number 9 is 4x squared y double prime plus 8xy prime plus y equals 0. Okay, so the initial polynomial, so this is Euler. Of course, we are in the chapter of Euler, but in general, you're going to have to look at what type of equation do I have here. Is this Bernoulli? Is this, well, that's first order, or is this separated variables? Again, that's first order, or what? Okay, whatever it is that we have seen. So initial polynomial is 4t times t minus 1 plus 8t plus 1 equals 0. Now we expand this as 4t squared minus 4t plus 8t plus 1. That is 4t squared plus 4t plus 1. And now you can try to find the factorization using the AC method. But if you know a little bit of, if you remember double products, this is a double product, right? Remember, a plus b squared is a squared plus 2ab plus b squared. Okay, the double product formula, and this is exactly what we get here. So we see what case are we in? We are in this case. Okay, and that's a special case. That's always has been a special case in all, even also when we dealt with the characteristic equation. That's so-called a single root, right? We have only the root. The only root is t equals minus a half. It has multiplicity 2. That use that fancy word that we introduced, and so it means something else has to be done. And what is the general solution? We know that the general solution looks like a times, what is the t? The t becomes the power of x to the power minus a half. But if we have two different roots, that's what we do. But if we have only one root, then we have the next possible one is ln x. Okay, so if you want to compare this, what happens with constant coefficient characteristic polynomial, instead of, here we take powers, there we take exponential powers. When we are in the special case that the discriminant is 0, we multiply with ln x. There we multiply it with x. And in the third one, you'll see, again, instead of plugging in x, we will plug in ln x. So if you want, the difference is between, the difference is kind of an exponentiation in both. But okay, that's not, well, you can read a bit more about it in the textbook if they prove why these things are true. But for us, we're just going to use this as a formula. And there was no initial condition in this case, but I said there could be initial conditions. Of course, the initial condition cannot be at x is 0. So I should point this out. So x is 0 is a singular point for this equation. And so, for instance, we cannot find you could say, why don't we just plug in a power series here, right? So let's see. This is not part of the homework, but I want you to see what goes wrong. If I try to put in here xn, so y prime is summation an xn minus 1 n, y double prime is summation n minus 1 an x to the n minus 2. And so, okay, if I now multiply, so we get, so we have to do 4 times x squared, so this is 4n n minus 1 an, right? That's 4 times this, and this gives me exactly x squared. That's what these Euler equations do. Plus 8 times n an, right? 8 times the x goes there, and the rest is there, the x to the n. So these are the power, so this is, okay, I'm going perhaps a little bit fast, but I mean to say this is the coefficient of x to the n. And so here we have just an, right? And this has to be equal to 0. Okay, so let's see what we get. We get an 4n squared minus 4n plus 8n plus 1. X to the n is 0. Okay, so, sorry, this is the coefficient. Each of these coefficients have to be 0, right? That's what it means. But this is not 0. This is, what is this? Well, this is 4, well, that's actually our initial polynomial, if you want. That's not by accident, by the way. But, so if this is not 0, this means that an has to be 0. And this is for all n. So if we try to put in a power series in here, we see the only power series that we can find is when they're all 0. Okay, when all the powers are, the coefficients are 0, which of course the 0 solution, yeah, true, the 0 solution is a solution, but it's not what we're after. There are other solutions, okay? So that is why we cannot use the method of power series at this game, and the reason is exactly because x is 0 is a singular point. So, meaning that you can use this if you would center your power series at anything else than the center 0. If you take center 1, then yes, you can work out from the previous setup. Okay, and I might ask you to do this on the quiz, for instance. Sometimes I mix a little bit of questions, right? Okay, let's look at the second case so that we have done both. Well, there's the first case I have not done discriminant positive, but for 12, that I think that, if I'm not mistaken, that is the x squared y double prime plus 3xy prime plus 5y equals 0. That's what I said, 12, right? Yes. Okay, so the initial, again, this is an Euler equation. So we, of course, as I said, we should check this, right? But we know that's what we are in here. So the initial polynomial is t times t minus 1. Right, that this part becomes t times this one becomes 3t, and this one becomes 5 is equal to 0. So t squared minus t plus 3t, that's plus 2t. I've done this in my head. Okay, I hope that's okay. And what we need to do now, well, you see, we can try to factor it, but multiply it to 5 and end up to 2 doesn't go. So soon you can suspicion that, oh, probably I need the quadratic formula. But in this case, it's sometimes better or easier sometimes to just complete the square. So we have t squared plus 2t. What do we do to complete in the square? We have to add 1 here, but then we subtract 1, right? We add 1, subtract 1, okay? And so this gives me t plus 1 squared plus 4 is equal to 0. And then t plus 1 squared is equal to negative 4. So that means that t plus 1 is equal to the square root of negative 1, that is plus or minus I, and the square root of 4 is 2. Okay? So we see that t is equal to minus 1 plus or minus 2i. So what we're dealing with is, again, there are two complex numbers. This is the real part, lambda, and omega is 2 is the imaginary part. And so what we now do is we get a solution. But now what the roles of these two guys in the characteristic in constant coefficients, this would be e to the lambda t, and this would be cosine omega t or sine omega t. Now it becomes, so the solution becomes x to the power that lambda, which is negative 1, Okay, so in general it is x to the power lambda cosine omega ln of x, or cosine or sine here, right? It could be either one. I don't need to say cosine or sine. Okay, so we get x minus 1 cosine 2x plus x minus 1 sine 2x, and of course with a and b's here. Okay. Sorry, I was focusing on I said ln x, right, and I plugged in x. That was silly. Ln x, and here 2 ln x. Okay. All right. So you can simplify this a little bit, but that's fine enough. Okay. Again, there were no initial conditions, I think, so I'll leave it like that. But I often like the initial condition. So just for the fun of it, suppose again the initial condition cannot be at 0. You see why? Because its function is not defined at 0, right? Ln, and also here I'm taking reciprocals. So if I plug in, let's do it at 1. That's always the easiest. So y1. So this is extra, right? I'm doing some extra here. Y1 say is, I don't know. That's y1 to be 2 and y prime 1 to be, I don't know, 4. I hope that works. So the only thing what we need, well, we can plug in. So this means if x is 1, then y is 2. That 2 is equal to a cosine of, the ln of 1 is 0. So the cosine of 0 is 1. So we get an a. And then here, the sine ln of 1 is 0. Sine of 0 is 0. So we get 2 is a. So what the real thing that we need to do here is, and for that I think it's a little bit easier if I factor it. If I factor out the x minus 1, I have to take the derivative, and that's a product rule. Or you could do also the quotient rule, but I am not fun. I am no fan of the quotient rule. So the derivative of the first one is minus x to minus 2. Copy the second. Plus x minus 1, and now we take the derivative of the second. There will be a 2 over x. This will be the derivative of the inside function. I'm writing that first. Then we have the a, and then derivative of cosine is minus sine. So we give a sine here to ln x. Okay, and the second one, let me perhaps do it in the order that you're more used to. So we have a b. Then the derivative of sine is cosine. Plug in the inside. Again, I'm copying it wrong. Ln x. And now take derivative of the inside function, that is 2 over x. Okay. So if I plug in now x is 1, and then we set that y prime is 4, we get 4 is equal to, now, all the powers of x are all going to be 1, and all the ln's are going to 0. So we get an a here from this part. This will disappear. Now, if I plug in 1 here, this sine will disappear, but the cosine will be okay. The x's I plug in 1, so that doesn't really matter. So we get plus 2b. Right? No minus sign mistake? No, I think I got it right. So, and we already had that a was 2. So this is 2. So 2 is equal to 2b. So we see that b is 1. Okay, so our particular solution here would be y is equal to x minus 1, or 1 over x, a, which was 2, right? Where was a? Yeah, 2. So 2 cosine 2 times ln x plus b, which was 1, sine 2 ln x. And that's our solution. And what you want, if you don't want the x minus 1, you can write it this way. Okay, this is if you have this additional initial condition that was not there in the homework. Okay, so this is not hard. You just have to make sure that you don't confuse. And yeah, I see that I again forgot to copy my ln's. I keep forgetting. Oh well, this 2 ln x, right? I keep copying it wrong here. It's so weird to have an ln inside of a cosine or a sine, right? But yeah, so the biggest risk here is that you confuse yourself with what happens with constant coefficients and characteristic equation. It's very, very similar, and there is a reason that it's so similar. There's a connection between the two, but okay. All right.